Welcome to Study Loop.
Okay, this is question 28.78. We have a pair of long, rigid metal rods here, each of length 0.5 meters, which are parallel to each other on a frictionless table, and they're connected by these two springs. Now, the springs have unstretched length L0, which I've actually just relabeled here J because it's hard to see. The L0 looks a little bit like a 10 here. So I'm going to just say unstretched length L0 or 10. And force constant K. And we're told, we have these two data points. We're told that when a current I runs through the circuit, the springs stretch by a distance of 0.04 meters, or 0.4 centimeters, which I've converted to meters here, so 0.004 meters. And when a current of 13.1 amps runs through this, we get a stretch here of 0.008 meters, 0.8 centimeters. So if we express this total distance d here between the two rods, then we can express this total d by j, or L0, that's this unstretched length, plus x, which is the amount that it's going to stretch. So this is what we're going to use. So in order to solve this, what we're going to need to do is think about the force between these two rods due to the magnetic field from the current. That force is going to be pushing the two rods away since these currents are running in opposite directions. And then the force of the spring is going to be pulling the two rods together. And so what we want, since we know that this whole system isn't moving, we want to set the force from the magnetic field equal to the force on the spring coming from the springs. So that will mean that our net force is 0, which is the state that our system is in here. So let's first take a look at the force between two wires. This is the general expression that we have here for the force per unit length of two wires with current I1 and I2. Let's just take a look here. We want just the force. We don't want force per unit length. So let's start by just multiplying by the length on both sides. That's just going to bring this over to the numerator here. Now I1 and I2 are actually both just equal to I because the same current is running through these two wires. So I can turn this I1 times I2 just into I squared up here. And now R is the only other thing we don't know, and R is the distance between the two wires. So the distance between these two rods here is going to be equal to D. So we're going to just set D there. And now the force from a spring, the force in general is going to be K times D. This is the force of a spring with constant K stretching over a distance D. But we have two of these springs acting on each rod. So I'm going to multiply that by 2. So we have 2kd is going to be the force pulling these two rods together. And this is the magnetic force pushing them apart. So now what we want to do is set these equal. So I'm going to come over here and set this equal to 2kd. And now we just want to rearrange this and simplify this a bit. So let's keep our mu naught I squared over here and multiply by 2 pi d on both sides. That's going to give us a 4 pi k d squared. And let's solve this for d. So if we take d squared, switching this the order here, we're going to have this in the numerator divided by our 4 pi k, I'm sorry, in the denominator. And so now if we want to solve for d, we're going to need to just take the square root of both sides. When we take the square root of this right side, we see we have an I squared, so we can pull one factor of I out, and we'll be left with this. Just 1 second. I'm going to draw the square root right here. So this whole thing, taking the square root. So now that we have this, all right, remember that our d is equal to j plus x, and we want to solve for j. J is our L naught here. So I'm going to put in j plus x in for d, and that's equal to I. And at this point, I'm just going to use the power of 1/2 instead of writing out this whole square root sign. Taking the square root is equal to raising to a power of 1/2. So I'm just going to write this just like this. So now let's take a look at what we have. For each value that we're told here, we're given I and we're given X. So let me just highlight this here. So we're given X and I for some given each of these points. And what we want to solve for is L0 or J and K. These are the two values that part A is asking us to find. So what we're going to do is we're going to plug each of these values in, and then that's going to give us two equations, and we'll have two unknowns, our J and our K. And we're going to have to solve that system of equations. So I'm just going to do that down here. I'm just going to plug in the two values that we know so that we can have our equations to solve. So we have our J, our L0, and that's plus 0.004, looking at this first equation. And the current in the first equation, or the first data point up here, is 8.05. And now at this point, let's just plug in the other things that we know too. So we know that the length is 0.5 meters. So I'm just going to plug that in here. So we know everything explicitly. And now we have everything up here except for K and J, which is what we want to solve for. And then just putting in the next data point, we have 0.008 for X and 13.1 here. And again, I'll put in 0.5. So these are the two equations we're going to need to solve for. Let's do that on a new tab up here. We have, sorry, let's just copy these, go over here. Okay, and remember our J is really our L0. I'll just put that up here just so we remember. Okay, so now we have two equations and two unknown variables, J and K. And there are a bunch of different ways that we can solve a system of equations. One way would be substitution, solve for one of these and plug it into the second equation. I'm going to do this by the subtraction method, where I'm going to write these, just going to put this one above, and I'm going to subtract the second equation here from the first equation, because there's one factor of J in each of these. And what that's going to do is cancel out our factor of J, leaving us just with K. So we can solve for K, plug that back in, and solve for J. So again, this isn't the only method to solve a system of equations, but this is one that's going to be pretty easy to use here. So basically, I'm writing this all out like one big subtraction here. So I'm taking this minus this. What that's going to give us is the factors of J are going to cancel out. So we're going to have 0.008 on this side minus 0.004. And then our right side is going to be this whole thing minus this whole thing. And notice that our factors here, this is the same in both. So what we're going to have out here is 13.1 minus 8.05. So hopefully this makes sense. We're just subtracting this from this, and this is all a constant in both of these two cases. So we can simplify this out a little bit. We're going to have 0.004 here. The left side is going to be pretty much the same, but we have the 13.1 minus 8.05 over here. So we'll have a factor of 5.05 out front. And this is the equation that we're going to solve. So this, you can just mu naught is a constant, so we can just rearrange this, square both sides to get rid of this, multiply by 4 pi k. I'm not going to do out all the algebra, but when you solve this equation, you should get k is equal to 0.08. So that's our spring constant. Now we want to find our J, or our L naught. So to do that, I'm just going to just pick one of these equations. It doesn't matter which one. I'll pick the first one up here. And what we want to do is just plug in the value that we just found for k, so 0.08, and solve this for j or for L naught. So we'll say L naught equals j equals 0.0024 meters, or 0.24 centimeters. So this is our result of just plugging this in and solving for j here. So this is the answer to part A. So now, looking at B asks, if I is equal to 12 amps, what distance x will each spring stretch? So to solve this, we want to go all the way back to our original equation with everything fully generalized. This one up here. Let's just do a new one over here. So this is our general equation, but now we know what j is. J is our L naught, so 0.0024. And we also know what k is now. So we know that k is 0.08. So now we have an equation where we can plug in I and get x. Just rearrange this and solve for x. Or alternately, we could plug in x and solve for I, because we only have these two unknown variables. So we are told in this case that I is 12 amps. What we just want to do is plug 12 amps here into this equation and solve for x. So to solve for x, we're going to need to just subtract this on both sides. And this gives us this whole expression for x. So again, I'm not going to actually plug this in, but you can just plug this directly into a calculator. Oh, we also know our L here. L is 0.5. So we have everything here that we need to solve for x, and we should get x equals 0.0071 meters, or 0.71 centimeters. So that's our answer for part B. Now for part C, we're asked what current is required for each spring to stretch 1 centimeter. So this is just the reverse case of this, where instead of having I and solving for x, we're told x and we want to solve for I. So starting with this same equation again, but now we know x is 0.01 meters because it's 1 centimeter. So we just want to plug in our expression here, 0.0024 plus 0.01, and that's going to be equal to everything here on the left side, on the right side, I'm sorry. So again, in order to solve this, what we're going to want to do, divide both sides by this whole thing, but these are all just numbers, so this can just be plugged in right into a calculator, and we should get that I is equal to 15.7 amps.